Hello everybody. In this video we'll go over the first part of section 4.3. We'll see what the derivative of a function tells me about the function. Then we'll go over the second part of section 4.1, which is the extreme value theorem. I will go over some definitions. We'll see what the first derivative test is. We'll do examples. Then we'll go over the statement of the extreme value theorem and we'll do some examples. Before we go over the first derivative test, we have to review the definitions of increasing and decreasing. So we see here that just by looking at this graph, it grows from left to right. So we say that this is an increasing graph. So then f increases. And we see that this is the case for if here I have x1, and then here this is x2, then here we have f of x1, and then up here we have f of x2. So we see that if a function increases in some interval, then for x1 less than x2, we see that f of x1 is less than f of x2. Okay? So then we see that in this case, the derivative is, right? So if we draw the tangent line, if we draw a tangent line anywhere here, we'll see that the slope will be positive. So we see that f prime is greater than 0, okay? So we see that the derivative will be positive in that interval, okay? Now, if we have a decreasing function, then it is the opposite. So in this case, we see that one more time, this is x1 and this is x2. So x1 is still less than x2, but we see that, for example, well, it's not so clear, but you can see that here, this is f of x1 and this is f of x2. So f of x1 is larger than f of x2. So I go here and I say, well, if I have a decreasing function, then we see that f of x1 is greater than f of x2. And here we say it decreases. And then again, if I draw my tangent line, I see that the slope is negative, therefore the derivative is less than 0. Okay, so here we see that the slope is negative. Okay, now if we have a constant function, then we see that here if we have x1 and we have x2, then we still have that x1 is less than x2, but we see that f of x1 is always equal to f of x2. That is the definition of a constant function. So we see that then f is constant. And we see that the derivative is 0, right? It's equal to 0 because the slope of the tangent line is 0, okay? Perfect. So now we're ready to go over the first derivative test. So in my last video, we saw that I had a graph that looks something like this, okay? Something like that. And then we saw that here we had a local max, and the derivative was equal to 0. Then here we have a local mean, and the derivative does not exist. And then here we have that the derivative is equal to 0, and we have a local max as well. Now we know that here before my local max, I have that the derivative is greater than 0. Here the derivative is less than 0. Here the derivative is greater than 0, and here the derivative is less than 0. And I know that for multiple reasons. The first reason is that, well, I know the definition of increasing and decreasing, and I know that whenever my function increases, the derivative is greater than 0. I know that whenever the function decreases, the derivative is less than 0, okay? So this is all the information we need. This is all the information we need for the first derivative test. This is exactly what it tells you. It tells you that if you have a critical number, and the sign of the derivative goes from positive to negative, then f evaluated at that critical number gives you a local max. If the sign of the derivative goes from negative to positive at a critical number, then f evaluated at that critical number gives you a minimum. So you have to keep in mind at all times that if my function has a local max or local mean, that local max, local mean comes from a critical number, okay? So we have enough space here to write this down. I'm going to write it. So this is the first derivative test. So I'm going to say, let C be a critical number of f. By that I mean, well, C it's in the domain of the function f, and the derivative is either 0 or does not exist. Okay, evaluated at C. Now, if C is a critical number of f, and on top of that, the sign of the derivative changes from positive to negative, we have a local max, so let me write it. So let C be a critical number of f. If sign of f prime changes from positive to negative at C, then f of C is a local max. Okay? If it changes from positive to negative, then we have a local max. Okay? Now, if it changes from negative to positive at C, we have this situation here. Okay? So if it changes from negative to positive at a critical number C, then f of C it's a local mean. Okay. Perfect. So let's do this example. We have to find intervals where the function increases and decreases, and then find local extrema. By that we mean find local max, local means. Okay. Now we know that whenever the first derivative is positive, the function increases. Whenever the first derivative is negative, the function decreases. Okay. So we're going to do this a little bit backwards. We're going to find the critical numbers. Okay, and then look at the sign of the derivative in between critical numbers and discontinuities. Why? Well, we know that if we have a local max, local mean, the sign of the derivative has to change at the critical numbers, okay? So that's a way of not only knowing whether the function increases or decreases, we also find local max, local mean that way, okay? We also have to look at the sign of the derivative if we had any discontinuities, because there's no reason why one side of the discontinuity has to agree with the other side of the discontinuity. In this case in particular, we're dealing with a polynomial. Polynomials are nice, okay? So we saw in my last video, so step 1, we're going to find critical numbers. Critical numbers. In this case in particular, we know that it's a continuous function. So we know that the critical numbers come from setting the derivative equal to 0. So I get that this is negative 3x squared minus 4x plus 15. And this is equal to 0 if and only if x is equal to 5/3 or negative 3. And this comes from my last video, so you can check that is true. Now, my second step, what I'm going to do is in step 2, I have to look at sign of f prime in between critical numbers and discontinuities. Okay? Okay. So I'm going to take this with me so I have more room. So what do I mean by that? I know that my critical numbers are 5/3 and negative 3, okay? So I literally take the x-axis and I go, okay, fine. I know that here I have negative 3 and here I have 5/3. So I want to look at the sign of the first derivative before negative 3, in between negative 3 and 5/3, and then after 5/3, okay? So I know that if the sign of the derivative will change, it'll change at either negative 3 or 5/3. Okay, so we take test values, a number before negative 3, we plug it into a derivative, whatever sign we get, that's the sign of the derivative in that interval, and we do the same for the other two. So let's just do it. So I'm going to go from negative infinity to I'm going to go from negative infinity to negative 3, then from negative 3 to 5/3, and then from 5/3 to infinity. Okay, and what I'm going to do is I'm going to take a test value. So I take a test value. That test value will plug into f prime, okay? So sine of f prime. And then depending on the sign, I'll know if the function increases or decreases. So information about f, okay? Perfect. So for test value, I need a number in between negative infinity and negative 3. I'm going to take negative 4. So if I do f prime of negative 4, I get negative 17. I don't care about the actual number, I care about the sign. So I get something negative. Since I got something negative, then that tells me that my function decreases in that interval. So it decreases from negative infinity to negative 3. Then I take a number in between negative 3 and 5/3. I'm gonna take 0, right? So if I take 0 as my test value, I do f prime of 0, I get that this is equal to 15. And then again, I do not care about the actual number. I'm looking at the sign. The sign of the derivative tells me whether the function increases or decreases. So I got something positive. That tells me that in between negative 3 and 5/3, my function increases. Okay? And then I take a number in between. 5/3 and infinity. So say, for example, I take 10. That's my favorite number. So if I do f prime of 10, then you get that this is negative 325. So I'm evaluating the derivative, okay? I'm plugging these numbers into the derivative. So I get something negative. The fact that I got something negative tells me that the function decreases. So I know that this function decreases and increases and decreases. So not only do I know the intervals where the function increases and decreases, I can also use this information to determine local max, local means, okay? So I know that using the first derivative test, since the derivative goes from negative to positive here, it goes from negative to positive at negative 3, then I obviously have a local min. So I know that f of negative 3, it's local mean. One more time. This critical number, the x value, tells me that f of that x value, it's a local max, local mean. When we talk about maximum minimums, this is the y value, okay? I hope that's clear. And then if we do the same thing using the first derivative test, then we know that at 5/3, the function changes, the derivative changes sign. It goes from positive to negative, so I obviously have a local max. Okay, so f of 5/3 is local max. Now, to answer the questions, we have to find intervals where the function increases, decreases, local max, local mean. So let me do it real quick. I know that f increases whenever the derivative is positive, right? So it increases from negative 3 to 5/3. So it increases from negative 3 to 5/3. F decreases whenever the derivative is negative. So from negative infinity to negative 3 and then 5/3 to infinity. So negative infinity to negative 3 and then from 5/3 to infinity. And then we know that f of negative 3, so f of negative 3, it's equal to negative 26 is my local mean, local minimum. And then f of 5/3, f of 5/3, f of 5/3, which is like 24.82, 24.81, it's my local maximum. Okay, perfect. Another example. Now we have that g of x is equal to x times e to a negative x. So step 1, we need to find critical numbers. Well, in my last video, we saw that this function has only one critical number at x equals 1, but I figured, let's just do it again, okay? So I know that g prime of x is equal to second one times the derivative of the first one plus the first one times the derivative of the second one, okay? So this is just equal to, I'm going to take e to the negative x out, and I get 1 minus x, and I know that this is 0 if and only if x is equal to 1. Now that tells me that I have to look at the sign of the derivative of this function before and after our critical number. If the sign of the derivative changes at 1, then we either have a local max, local mean, depending on whether it goes from positive to negative or negative to positive. Okay, so let's do that. So step 2, sign of g prime in between, well, critical numbers, which again, we only have 1, and discontinuities, and we don't have any. Okay, so let's make my little table here. So I know that I'm going to go from negative infinity to 1, and then from 1 to infinity. And like we did before, I'm going to take here a test value. Take a test value. I look at the sign of g prime, and then what information we can get from the sign of the derivative when it comes to the behavior of the graph, okay? Perfect. So I take a number in between negative infinity and 1. I'm going to go with 0. So if I do g prime of 0, so I take 0. If I do g prime of 0, I get 1. So g prime of 0 is equal to 1, which is, it's positive. Since it is positive, that tells me that my function g increases from negative infinity to 1. Now, we take a number in between 1 and infinity. Let's take 2. We do g prime of 2, and we get that g prime of 2 is equal to negative e to the negative 2. So it's negative, so it decreases. So what you have to keep in mind is that the sign of the derivative changes at 1, okay? The sign of the derivative goes from positive to negative at 1, so that tells me that my function evaluated at 1, that's the maximum. So one more time, the derivative tells me what the maximum of the function is. Is that clear? So what I'm saying is that g of 1 is local max. Okay? So then I know that g increases from negative infinity to 1 because the derivative is positive. So g increases from negative infinity to 1. G decreases from 1 to infinity, and then g of 1 equal to, so g of 1 equal to e to the negative 1. It's my local max. Okay? So one more time. If you're trying to see whether the function increases, decreases, you're going to plug into the derivative. If the derivative is positive, the function increases. If the derivative is negative, the function decreases, okay? If the derivative goes from positive to negative, then at that critical number, you have a maximum. But the maximum belongs to the function, okay? So if you're going to find the actual maximum, you have to plug into the function, not the derivative. Is that clear? The function, not the derivative. Okay. Perfect. Now let's do another example, which is very cool. So now I give you this graph, and I tell you, hey, look, this is the graph of a function of the derivative of a function f. The function is defined everywhere. Okay, the function is defined everywhere, but this is the graph of the derivative. This is the graph of the derivative of my function, and I want to use the information that the graph of the derivative gives me about the function to answer the following questions. So first we want to see what else. We want to determine any critical numbers. We want to find intervals where the function increases and decreases. And then we want to find the x-coordinates of the local extrema, meaning any local max, local mean. In order to do this, we have to understand the definitions, okay? We have to understand that we have critical numbers whenever the derivative is 0 or does not exist, and they have to live in the domain of the function. Well, in this case, we know that f is defined everywhere, okay? So if we find places where the derivative is either 0 or does not exist, then we know that those are my critical numbers, okay? Perfect. So I know that the graph of a function, whenever the graph it's above the x-axis, the function is positive. In this case, this is the graph of f prime. So above the x-axis, we have that f prime, it's positive. Below the x-axis, we have that f prime, it's negative. And then on the x-axis, we have that f prime, it's equal to 0. Okay? So we look at the graph and we see that the derivative is equal to 0 at -3. The derivative is equal to 0 at 3. And the derivative does not exist, or it's not defined, at 1. Okay? Not defined. So f prime not defined, f prime equals 0, f prime equals 0. So that tells me that those are my critical numbers, okay? So my critical numbers are, critical numbers, x equals -3, 1, and 3. So if I want to see the intervals with the function increases, decreases, and any local max, local mean, then we make our table, okay? So I'm going to make a little table here. I'm going to go from, well, in this case, it goes on forever. So I'm going to say from -infinity to -3, then from -3 to 1, and then from 1 to infinity. Okay. We don't need a test value, so we can go straight to the sign of f prime. Again, if it's above the x-axis, then it's positive. If it's below the x-axis, then it's negative, okay? And then information that we get about f. Okay, so let's see. From -infinity to -3, from -infinity to -3, from -infinity to -3, my function is below the x-axis, okay? One more time, from -infinity to -3, the function is below the x-axis. So we see that, so this is below x-axis. Since it is below the x-axis, that tells me that the derivative is negative. So I go here and I say from -infinity to -3, the graph of f prime is below the x-axis, meaning it's negative. So the derivative, if it's negative, tells me that the function decreases. Now I go from -3 to -1, from -3 to from -3 to 1, from -3 to 1, my function is above the x-axis. So it's above x-axis. Since from -3 to 1, the derivative is above the x-axis, then we know that it is positive. The fact that the derivative is positive tells me that my function increases. And then from 1 to infinity, the function is below the x-axis. Wait. From 1 to 3, the function is below the x-axis. It is below the x-axis. So here I have to fix this. So this is from 1 to 3. And then from 1 to 3, the function is below the x-axis, so the derivative is negative, so it decreases. And then now I look at what happens from 3 to infinity. From 3 to infinity, I have that the function is above the x-axis. The function is above the x-axis, so it is positive. Okay, so you don't see it, but I can move it. Okay, or not. I can just take the whole thing with me. There we go. Okay. Perfect. So since it is above the x-axis, then we know that it is positive. So the function increases. And I know that if the sign of the derivative changes from negative to positive, you have a minimum, and then a maximum, and then a minimum. So then that tells me that f has local means at f of -3, f of 3, which is the places where the sign of the derivative changes from negative to positive, okay? And then f has local max at f1, which is where the sign of the derivative changes from positive to negative, okay? Perfect. So now we go over the second part of section 4.1, which is the extreme value theorem. And I hope it makes sense why I do things in the order I do them, because I think once you understand local max, local mean, and you understand the first derivative test, then understanding the extreme value theorem is trivial. So check this out. So I'm going to draw a graph here. It doesn't really matter what it looks like. So I'm going to go with something like this, and then like that, and then like this, right? That's my graph. I'm going to call this f. This is the graph of f of x. Now, if you look at it, then you'll see that here, we see that here, whatever this value is, this is a local max, right? And this is a local mean. We have a local max, we have a local mean. Now we have no absolute maximum because this keeps growing. So no abs max. And we have no absolute minimum because this keeps going to negative infinity. So no abs min, meaning you can always find a smaller value of y, okay? Now imagine for a second that instead of taking the whole graph, now I restrict the domain, okay? So now say, for example, I do this. Now I take, instead of taking the whole thing, I go, okay, fine. I will consider my function from here to here, okay? So if I only consider the function from whatever this, I'm going to say A and B, from A to B, and I ignore everything else, then we get this. So we get that graph, okay? We get this graph. So that tells me that. Now, can we find absolute maximum and absolute minimum? Absolutely, right? So you look at this, and just by looking at it, then you see that this still is my, so now this here will be my absolute minimum. And this will be my absolute maximum. And this is the extreme value theorem, okay? And this is exactly what the extreme value theorem says, okay? If I have a continuous function on a closed interval, then I will have both absolute maximum and absolute minimum, okay? This theorem, it's what we called an existence theorem. So it tells you that if you have a continuous function on a closed, it has to be closed interval, then you will have absolute maximum and absolute minimum. You'll have both. What this does not tell you is how to find them, okay? But from the graph, it's easy to see that the absolute maximum, absolute minimum will happen either at the critical numbers or the endpoints, okay? So note, absolute maximum and minimum. have been at critical numbers. Critical numbers in A, B, right? Or the endpoints. Okay, perfect. So steps to find absolute maximum and absolute minimum of a continuous function on a closed interval, right? Of a continuous function over a closed interval a, b, okay? This is super important, okay? So step one, find critical numbers in a, b. I'm going to call them C1, C2, all the way to Cn so that I can refer back to them. Step two, I'm going to say of a continuous function, I'm going to call it f so that I can write this easier. Okay, so function f. So then the second step, what you do is you go, okay, you substitute every single critical number that lives in between a and b, and you also do f of a and f of b, meaning you substitute the endpoints into the function, plug them into the function, and then the largest is your absolute maximum, and then the smallest is your absolute minimum. Okay, so let's do an example. So now we have to find absolute maximum, absolute minimum of my function x times e to the negative x in between -2 and 0. Okay, we know that this is a continuous function and we are given a closed interval, right? We are given a closed interval. So let's follow the steps. Well, step one, critical numbers. Step one, let's find critical numbers. We'll just use red for this. Okay, so step one, critical numbers. Critical numbers that live in between, so critical numbers in -2, 0, okay? It has to live in between -2 and 0, okay? So we saw that f prime of x is equal to 0 if and only if x is equal to 1, okay? But this is not in -2, 0, so I will not consider 1 in my next step. Step two, you substitute the critical numbers and the endpoints. So step two, what do we get when we do f of -2? What do we get when we do f of 0? And then the largest will be my maximum, the smallest will be the minimum, the absolute maximum, absolute minimum. So let's see. So okay, my function evaluated at -2. I get -2e squared, and then I get 0. Okay, so this is a negative number, so that's smaller than this. So that tells me then that -2e squared, this is my absolute minimum, and 0 is the absolute maximum. Okay, is the absolute maximum in this interval. Okay, you have to keep in mind we're looking for absolute maximum, absolute minimum in some given interval. Okay, I'm not claiming that this is the absolute maximum, absolute minimum of the function in the real numbers. I am restricting this to -2, 0. Okay. So now we have this polynomial -x cubed minus 2x squared plus 15x plus 10 from 0 to 10. And we saw that this function, this polynomial has critical numbers. So step one, critical numbers. we saw that f prime of x is equal to 0 if and only if x is equal to negative 3 and 5/3. Okay. Now we're looking at the absolute max, absolute minimum from 0 to 10. So that tells me that negative 3, we don't take it into consideration when we go to the second step because it is not in between 0 and 10. Okay. Now step two, we'll look at the value of the function at my critical numbers in between 0 and 10 and the endpoints. In other words, I want to find what f of 5/3 is. I want to find what f of 0 is. I want to find what f of 10 is. One more time, I'm plugging 5/3 because this is a critical number. And I'm plugging 0 and 10 because these are the endpoints. Okay, so here we go. Okay, so we do f of 5/3. I get f of 5/3. I get 24. I get 24.81. If I do f of 0, I get 10 obviously. But if I do f of 10, I get negative 10. I get negative 1040. Okay. So then you go back and you look at this and you see that, well, negative 1040, that's the smallest of all. So this is my absolute minimum. So absolute minimum. And then 24.81 is the largest of all. So this is my absolute maximum. And that's it. I hope this makes sense. And again, thank you for watching. I'll see you next time.